Introduction. The enclosure material for an enclosed busbar system is generally aluminium alloy sheet, extrusion or sheet steel. Stainless steel and fiberglass enclosures have also been used for very specific requirements. The enclosure contributes a significant part to the overall cost of the product and must, therefore, be optimized. The enclosures have to be fabricated, painted, assembled with components, installed at the site, and should require minimum maintenance for the entire life of the enclosed bus. To be cost-effective, the enclosure material properties must consider workability and weldability. Fabrication of enclosure comprises shearing, punching, folding, and welding. The process can be manual or automated and contributes significantly to the cost and performance of the product. Strength. The enclosures are expected to withstand internal forces generated by a short circuit and external forces caused by wind, snow, ice, vibrations, and seismic activity. Resistance to corrosion and erosion. Enclosures are subjected to corrosion and erosion depending upon the service conditions. Surface coats provide additional protection and enhance life. Gas-insulated bus with aluminium enclosure may be buried below ground. Apart from providing surface protection with coats, sacrificial anodes, and cathodic protection are provided to counter the effect of corrosion. Electrical conductivity. Enclosure material with a higher conductivity is advantageous as it will contain losses and act as an electromagnetic shield. In many designs, where enclosure also serves as an earth conductor, higher conductivity is preferable. Enclosures of isolated phase bus carry the current almost equal to that of the conductor, and to limit the losses and temperature rise, they are fabricated from high conductivity aluminium. Losses. All metallic enclosures of the busbar systems will generate eddy current losses, and those with steel will, in addition, generate hysteresis losses which contribute to a temperature rise of the enclosure. All international standards specify a limit on the temperature rise of the bus enclosure. Weight. The enclosure contributes significantly to the overall weight of the enclosed busbar system. Manufacturers have a preference for aluminium over steel. The lower overall weight facilitates ease of installation and lower cost of the support structure. Comparative properties of aluminium and steel, MKS units, are detailed in Table 2.1a. These include electrical conductivity, electrical resistivity, temperature coefficient of resistance, thermal conductivity, specific heat, melting point, density, temperature coefficient of expansion, modulus of elasticity, ultimate tensile strength, relative permeability, skin depth. Comparative properties of aluminium and steel, FPS units, are detailed in Table 2.1b. These include electrical conductivity, electrical resistivity, temperature coefficient of resistance, thermal conductivity, specific heat, melting point, density, temperature coefficient of expansion, modulus of elasticity, ultimate tensile strength, relative permeability, skin depth. Aluminium alloy. Over the last few decades, aluminium welding technology has vastly improved, bringing down the cost significantly. Furthermore, the cost of the dies for extrusion of aluminium has drastically come down. Aluminium sheets are available in various alloy compositions, and it is possible to select a specific alloy for the desired application. Alloy sheets are available with a conductivity of 61% IACS with less mechanical strength to 30% IACS with 60% of the strength of steel. Alloy sheets are available with excellent resistance to corrosion. This flexibility has made aluminium sheets and extrusions the preferred material for bus enclosures. Aluminium tubes are extruded up to a diameter of 600 mm, 24 inches. Extruded tubes are preferable to rolled tubes. Marginal loss of conductivity can be compensated by an increase in thickness for an envisaged resistance. Extruded pipes have better mechanical properties. The process of extrusion demands a minimum T/D, thickness to diameter, ratio. For long route length of bus enclosures with a larger diameter, as may be required for gas-insulated transmission line, a spiral welding sheet is adopted. Grades 1050 and 1350 have excellent conductivity, while grade 6101 exhibits good mechanical properties at a marginal compromise with conductivity. Grade 5052 displays good properties for corrosion resistance, workability, formability, and weldability. Grade 6061 is extruded and displays good mechanical properties. These alloys can be heat treated and are available in different tempers. Depending upon the nature of specific requirements, with respect to conductivity, mechanical properties, and resistance to corrosion, enclosure material is chosen from a wide range of treated alloys. Busbar systems manufactured with aluminium enclosures are lighter. Aluminium enclosures provide excellent earth continuity. Special aluminium alloys are used when enclosures are exposed to saline atmospheres, as in installations in coastal areas, ships, and offshore platforms, or when the gas-insulated bus are buried underground. Steel. Powder-coated sheet steel is used extensively as a bus enclosure material. Steel is economical, strong, and workable. The sheets are cold rolled up to a thickness of 4 mm, 5 by 32 inches. Since steel enclosures are more susceptible to corrosion, it has now become a normal practice to fabricate the enclosure with galvanized sheets to provide better environmental protection. Powder coating of galvanized sheets, to the desired color and finish, provides additional protection. Busbar trunkings, installed for the distribution of power in an assembly area or machine shop, are invariably made with steel enclosures. These are characterized by low rated currents and low fault currents, and therefore are not subjected to significant electrodynamic forces. The overall cross-section size is small. Since the weight of the busbar trunking, enclosure plus conductor plus insulating support, is low and is installed indoors, it is not subjected to large mechanical forces. The enclosures for these are made from steel of thickness as low as 1.0 mm, 3 by 64 inches. The entire enclosure is formed, profiled, to provide adequate strength. Tap-off boxes with thin sheet steel enclosures, equipped with isolating and protecting devices, are attached to the main trunking. Stainless steel. There are some extremely corrosive atmospheres where clients prefer stainless steel for bus enclosures. Chlorine and saline atmospheres aggressively corrode steel and aluminium enclosures. Stainless steel is the preferred material in offshore platforms and chlorination plants. Drug and pharmaceutical industries specify this material when the enclosed bus runs inside the plant. Stainless steel sheets and components are manufactured in two grades, Type SS304 and Type SS316. Both are austenitic steel and have very low magnetic susceptibility. Grade SS304 exhibits more magnetic property than grade SS316. As a crude approximation, both of these can be called non-magnetic and hence do not generate hysteresis losses in presence of the magnetic field generated by alternating currents. Stainless steel sheets are more difficult to work with. Being a hard material, they require special tools, drills, dies, and punches. Metal inert gas or tungsten inert gas welding needs to be performed during manufacture. Stainless steel enclosures are expensive to manufacture and hence specified only for very special needs. Stainless steel enclosures, manufactured with grade Type SS316, have a higher corrosion resistance due to the presence of molybdenum and a higher content of nickel than grade Type SS304. The preferred material for stainless steel hardware is SS304 that has higher chromium content and is therefore much harder and wear resistant. Stainless steel enclosures do not require painting, unless it is required to improve emissivity for better heat dissipation. Stainless steel alloy composition for type grade SS304 and grade type SS316 is detailed in Table 2.2. The alloy elements comprise carbon, manganese, phosphorus, sulfur, silicon, chromium, nickel, and molybdenum. Enclosure losses. Any metallic object in the vicinity of a current-carrying conductor will have induced losses. All enclosed busbar systems have metallic enclosures. Non-magnetic metallic enclosure, such as aluminium or stainless steel, will generate eddy current losses. Magnetic metallic enclosure, such as sheet steel, will, in addition to the eddy current losses, generate hysteresis losses. Metallic segregation, if provided between the phases, will also generate losses and are considered as part of the enclosure losses. These losses are sometimes referred to as parasitic losses. Enclosure losses increase with the increase in the conductor current. Along with the conductor losses, enclosure losses contribute to the temperature rise of the enclosure, which is one of the constraints in the design of an enclosed busbar system. Certain types of enclosed busbar systems, such as continuous type isolated phase bus, generate losses due to intentionally induced circulating currents. These losses will be fed by the source to which the busbar system is connected. The magnitude of the enclosure losses as a percentage of total losses depends upon the type of busbar system. Enclosure losses in non-segregated and segregated phase bus also depend upon the type of construction of the enclosure and earthing scheme. The enclosure currents are not uniform along the length of the bus duct and can result in increased current densities in certain locations. Eddy current losses vary with the conductivity of the enclosure material. The skin depth of steel is 40 times less than that of aluminium. It is therefore obvious that a thicker aluminium enclosure or a thinner steel enclosure will generate fewer losses. Hysteresis losses will decrease with the decrease in the thickness of the steel enclosure. The above phenomenon has dictated the choice of the enclosure material for different types of busbar systems. Table 2.3 details the recommendations for the enclosure material for different types of busbar systems. Where alternatives are acceptable, the selection of the enclosure material will be governed by specific requirements of mechanical strength and resistance to corrosion, provided its temperature at the hotspot under rated conductor current meets the specification requirements. The enclosure may be given a coat of paint for additional environmental protection and improved emissivity. Enclosures of isolated phase bus tap-off connections to surge protection voltage transformer cubicle, excitation transformer, and auxiliary transformers run at temperatures that are significantly lower than the specified maximum temperature when operating under rated conductor current. These connections are more often sized to withstand the short time current for the specified duration. The relative size and phase spacing of the tap-off enclosure are small, while it is subjected to the largest magnitude of short-circuit current in a generator connection. The enclosure needs to withstand very high electrodynamic forces. An aluminium alloy enclosure material with a lower conductivity, in exchange for a higher mechanical strength, is in order as long as it meets the specified temperature rise requirements. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the Founder Director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.